Now we're going to take a look at a function which you probably haven't seen in previous classes, and that's the Sinc function. It's pretty simple to define, but it turns out to be very useful when trying to think about bandpass filters and other types of filters that we're going to look at in this class. So learning objectives here are to basically be able to understand what the Sinc function looks like, and to be able to sketch it and figure out where it crosses zero, because essentially those are the important things to know about drawing the Sinc function. Okay, so here is the Sinc function. It's pronounced Sinc of t, and it's just sine pi of t over pi t. Now this is how electrical engineers and people in engineering and communications define the Sinc function. Sometimes in calculus, if it gets used, it's defined as sine t over t, but we're going to put the pi in there because the pi is useful for being explicit about when we talk about frequencies. So sine of pi t over pi t. What does it look like? It looks like this kind of, I don't know, I think it looks sort of like an octopus, in profile. It's this wiggly little function. It looks like a sine wave, but it's being damped by 1 over t term, so it's decaying pretty fast. So like those complex exponentials that we saw before, or rather these decaying exponentials multiplied by a sinusoid, but here it's 1 over t. So what's the value at t equals 0? Well, to understand that, we're going to have to use a little bit of calculus. In fact, we're going to have to use L'Hopital's rule, which says that if we want to look at the value at 0, since sine of 0, sine of pi 0 and pi 0 are both equal to 0, we have to, if we want to know what the ratio is, we should take the ratio of the derivatives and send the limit as t goes to 0. And if you do that, you get just 1. So the Sinc function is 1. Our little octopus starts out at 1, and then it wiggles around, crossing the axis. And the next question we want to ask is, where does it cross the axis? The Sinc function is 0 at every non-zero integer value of t. That's because the sine function, when you look at sine of pi t, basically if t is an integer, then you get sine of pi times an integer, and that's 0. So we just get 0 crossings at every non-zero integer value, because at 0 we just calculated what the limit is. So Sinc of 0, remember Sinc of 0 is equal to 1. So, when we think about our octopus, here's our little guy here, these 0 crossings, so this is going to be at 1, 2, 3, and so on. Now what if I scale the function? If I look at Sinc of alpha times t, well, that's sine of alpha pi t over alpha pi t. And that's just 0 whenever t is an integer multiple of 1 over alpha. So it's pretty straightforward, and it's easier to see when we take a look at a picture of it. So here's our Sinc function. It's we can get a thin, wigglier octopus, or a wider, more stately, slow-moving octopus if we depending on whether we multiply by 2 or divide by 2 in the time function. So we can see that the 0 crossings move to k over alpha. So here in the left side, we see that we're going to have a 0 crossing at a half, and then at 1, and then at 3 halves, and then at 2, and so on and so forth. Whereas over here, we're going to get them at 2, 4, 6, and so on. And same on the negative side. So this is how you can understand what stretching and squishing the Sinc function looks like. And so you can see, it gets a bit more high frequency when you squish it, and a little bit lower frequency, kind of more mellow, when you stretch it. The Sinc in discrete time is defined the same way. We can define the Sinc of n as sine of pi n over pi n, and just think of it as a sampled version of the CT Sinc function. But more often, we're just going to write it out instead of using this Sinc shorthand, because we actually care about changing the numerator part and not so much the denominator part. So we'll see things like h of n is equal to sine pi over 4n, or more in general, kind of like sine of omega naught n over pi n, and that's going to turn out to be related to some of our low-pass filters that we saw kind of demonstrated earlier. And if you want a little exercise for yourself, try to determine the value of this h of n, so the value of h of 0, by taking the limit of the continuous time version. That can be a little bit of an exercise for yourself. So this is a quick introduction to the Sinc function, and we're going to see it a little bit more later in the course. So just hold on to your seats.